Hi, I'm Kaden Korn, and this is Georgia Tech Lab 1 on constant velocity. First, I'm going to talk about the timeline. We're going to have an introduction, then I'm going to go over the models, the main experiment, the coding, the discussion of the results, and finally the conclusion. So first of all, I want to talk about the purpose of this lab, which is, to discover and compare an object with constant velocity and to develop a computational model based off of this without any net force creating an acceleration. This uses fundamental principles such as Newton's law or basic interactions. Yeah. So the key concepts are Newton's first law, which is sorry about that. The first law says that an object in motion stays in motion, whereas the second law says that the force on an object is equal to its mass times its acceleration. This means that the heavier an object is, the more force that is needed to move or speed up the object. Therefore, the more force that you apply, the more acceleration an object will experience. Lastly, I want to go over the concept of constant velocity, which is shown by net force 0 at the bottom. Basically, since net force is 0, according to the equation F equals ma, no acceleration can be experienced. There will be some necessary equations that should be known for this experiment, which is the velocity update formula, which is velocity final is equal to the initial velocity plus the net force over the mass times the change in time. This equation is being used for this experiment because the net force acting on this system is 0, so the velocity will not be able to change under those rules. There is also other equations that will be needed, which is the position update formula and the average velocity formula. We can use the slope to determine the average velocity of the cart. The position update formula is used in the computational model to update where the cart is at each frame. This is the graph of x versus t, and these results show that the experimental model confirmed that the object moved with constant velocity, shown by the general linear pattern here. But I want to back up a little bit because I want to go over systems versus surroundings. The system here is the cart or marker. The surroundings are any external factors like friction or air resistance. The experimental position is the tracker. Predicted position is glow script. And lastly, the results were moved into Excel. So this is the general procedure. Step 1 would be to record. This involved making sure to get a clean recording from a vertical view so that no camera distortion affected results. Second is to put this video into Tracker, which involved actually getting to know how to use Tracker as well as actually operating on this code. 3 is to use the model with the starter code and change it to match my own experiment. That way I could run the model and get the results that I wanted. And then lastly, I needed to output these results into Excel so that they could be analyzed. The initial conditions for this experiment were determined. The initial conditions for this position were determined using a scale reference in Tracker. The initial velocity conditions were determined from the slope of the position versus time graph shown on the screen right here, and also through Tracker. The total time for the cart to move from the start to finish was 2.66 seconds. The initial position was 0.015 meters in the x direction. The initial velocity was calculated to be 0.462 meters per second. This was calculated from the change in position over the change in time from the first two time frames. These data points were then used to develop the computational model. Oops. This was the graph that was produced. Let's take a look at this graph together. Shown here is position versus time graph of the cart's predicted and experimental position. As you can see, the results support my analysis because the graph is generally linear. This tells us that it had constant velocity and that there was generally no acceleration and that net force was close to zero. This is consistent with Newton's second law because obviously there's no major force acting on it, so it should be linear. So let's take a look at a couple sources of error. As I was just talking about, friction and air resistance can change what's going on. So, for example, there may have been a force in the positive x direction and friction was canceling it out, or any number of canceling net forces that we don't know about. And the next is human error. Pushing the cart is obviously a insecure way of doing this experiment. So there could have been error in the way that we measured. So what does this experiment really mean? What are some takeaways here? First of all, I want to look at some hypotheticals. If you flipped the axes, velocity would still be constant, net force would be zero, but the signs would be flipped. And this is important because it basically proves that Newton's law will uphold in all positions on the planet, and just that the signs will swap because the vectors are different. In conclusion, Newton's second law is supported by this experiment. It is important to mention that this conclusion doesn't mean that no forces were acting on the object, but simply that if there were forces, they were generally canceling each other out. It's also not perfect because of the sources of error and that there's negligible differences that the camera can't pick up on and in between frames and things like that. So the results are not 100% secure, but the experiment is in favor of supporting Newton's second law. Thank you.